Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and it is always an honor and privilege to be serving you as you learn some math with me. Come step into my virtual classroom. Today we are going to be looking at graphing representations, and what that means is basically looking at a real-world kind of problem context and looking at what it means, what that graph represents, how we can sketch a graph based on a representation with two categorical variables, something on x, which is normally time, something on y, like a height, a distance, a weight, a value. You'll see a bunch of situations here. I have 22 practice problems, probably like 6 or 7 different graphs, and they're just broken up in parts with the questions. And I want to go over these things with you. We'll be covering what they represent in each part, a domain and range kind of thing, discrete versus continuous. Let's go ahead and get started with this. And I'm going to give you here, I think, 4 questions on this first bit. The graph shows the attendance at a hockey game and the rate at which the fans enter and exit the arena. And problem number 1 is going to be asked, and then I have a number 2 based on the same graph, etc. Okay, so just looking at this graph really quickly so we understand what we're looking at. Something about a hockey game and the attendance and time. Now, they don't give you actual numbers, and by and large, that's pretty much okay. We just have to get the overall gist of what's happening. At the start of, maybe not even the hockey game, but at minute number 0 and what we're tracking, nobody is in the arena yet. And that's probably because this is the time when it was still closed. And then at time 0, I guess it opens and people start pouring in. Okay, so that's that's something there, and I could describe the entire thing, but I'm sure they're going to be stating some things within. I just want to make sure you got that. And at the end of segment 9, it looks like everybody's left and they're getting ready to lock up. So whatever minute number that is, that doesn't really matter. It could be minute number 200 or whatever. The point is things happen and we want to be able to explain them. I want you to know I haven't seen these questions yet. I set them up, but I haven't read them. So you might see me not struggle, but really work through different things that spontaneously pour through my mind. So let's take a look right now. I haven't seen these questions yet. Number 1, compare segments 1 and 2. What do they represent? So okay, so this is the part that I was just talking about before. Segment 1 looks like fans are starting to really enter the arena. And segment 2, fans still are kind of entering the arena. The number of people is going up as time goes on. And you need to really make sense of time being a physical thing here, like a timeline. As time goes to the right, as more minutes go by, people are starting to attend. So minutes numbered 1 and 2, I guess they're representing fans entering arena after opening. Now, what could describe why number 2 is slower than number 1? Probably because number 1 is that first wave of, tailgaters, people who are at the arena then and in the parking lot or waiting in line to come in. And then it probably slows at a decent rate. Maybe they need less employees out there to be putting people in and it slows it down. Or these are people who are kind of just arriving. It's less of a pour. Think of like the launch of like a new iPhone or something. And what happens in those situations. You're looking at people who pre-order, like who are waiting out in line, right? They're waiting out in line for days. And not everyone buys at the same moment, but you get a mad rush in the beginning, and then some people are trickling in getting it thereafter, if that kind of makes sense. All right, so let's go ahead and take a look at question number 2, and let's see what it asks. What does segment 8 represent in terms of the game? Again, this might be a scenario in segment number 8 where you could say that the game ended right here from game 7 to game 8, whatever minute, game 7, segment 7 to segment 8, whatever minute that was. All the fans left because the game ended. That could absolutely be a scenario because I have 2 in mind that I'm thinking about this. So A, what does it represent in terms of the game? It could mean game over, fans leaving. And that's, I think, my preferred one because if you're talking about, many people might not consider the second option that I'm going to say. I think most people would probably say this. This is the highlight of the game, and then, some people maybe kind of left, whatever, and then game over. I think that's really my preferred one. Option B is something like, it's that moment, and this is a hockey game, so I got to put in hockey terms. It's that moment where, like, that, oh gosh, what's the term? That goal that was like, the dagger. That dagger goal was scored by, like, the opposing team. And everyone's like, that's it. We're done. We're out of here. And most people leave. And then there are people in segment 9 that maybe like stick around just a little bit. And they're like, oh, no, wait, I want to support the team and watch that. So segment B, it could be something like the blowout moment. The moment near the end of the game where you say, we can't come back. I'm sure it's more of a part A thing. Game finished. What could explain why Situation 9 fans pour out a little more slowly there, or people are still there? Some people hang out, whatever. Post-game interviews, take some photos, souvenirs. It could be that. So keep that in mind. Question number 3. What is the significance of segments 5 and 7? And they're not asking what kind of situation is being represented in terms of what caused this to happen, but what they're asking is what is actually taking form here? That there is a constant number of people in the stadium. And I think I kind of just answered it. There's a constant number of people in the stadium. Nobody is entering and nobody is leaving right here. I suppose if we could really talk about extreme context significance of segment number 5, this is the high point in the stadium. Everyone's arrived, right? The game has started. Everyone's arrived. No more traffic and entering, whatever. Everyone's there. This is really not the high action, but the point where, everyone's arrived, right? So, but what they're, and segment 7, again, people are sticking around. There are some early birds who are like, yeah, let's get out of here. People are sticking around, and here's the high action. Third period. There are 3 periods in hockey. But what is the significance of the segments? No fans are entering or leaving. By the way, speaking of fans and such, the A's game is behind me. It's the bottom of the 9th. I want to check out that score in just a moment here. Let's see what's going on. I think it's 5-1, bottom of the 9th. Yeah, A's have 2 outs. They're about to be out of contention. This is the wild card game. Rays are about to advance to the ALCS. One thing I like about baseball, compared to that of hockey, soccer, football, basketball, anything like that, is you earn your offense up there. The more you hit, the more you get to stay up on offense. There is no time. So, realistically, there is no dagger, home run, or run scored, or strikeout, or whatever in this thing until the game is over. They could hit 4 more home runs here, and it's actually conceivable. They don't have 5 minutes to do that. That is something I love about baseball. Do I think it's going to happen? No, the probability is very low. But, never taking it out of contention. All right, question number 4, what does segment 6 mean? Now, again, it means fans are leaving the arena very slowly. This is the slowest rate in which fans leave, or segment number 9. But I think they're also asking for context, so I'll put in 2 things. Few fans, how about this? Few fans leaving the arena. Why might this be happening? It might be getting late in the evening. Hockey games tend to play kind of late. Maybe the kiddos got to go to bed and it's a school night and parents are bringing some of them home. Maybe it's maybe it's an afternoon game and they want to miss traffic or whatever. The early birds are leaving, basically, is what's happening here. For whatever reason, a couple people phased out. And it happens all the time. I've done it too. Not wanting to, but I've done it before. Or consider this. And, it's kind of the same thing, but consider this. Maybe this game went into overtime. Oh, look, the Rays won. Oh, well, you're going to watch some Sports Center behind me here. Maybe the game went into overtime. Maybe at the end of segment 5 is when when regulation actually ended. And some people maybe leave. Some people maybe believe that the game can end in a tie right then and there. And they're like, oh, let's get out of here. Or they're like, we stayed for 3rd periods. We committed. We got our money's worth. We're good. And then number 7 could be overtime. Something like that. So there are a lot of different things that it could represent. But just early birds leaving, I'm fine with that. Now, I like to talk over these things right here because there's so many things that you could mention. So sorry if the time kind of trickles up and takes a while because I want to have a conversation about it. This is the first time I'm seeing it. I'm seeing these questions. And I think that's it for these things. Yes. All right. So next scenario here, question number 5 and maybe 6 and 7, etc. We use 5 through 8. Graphs A through D are here for questions 5 through 8. Janelle alternates between running and walking. She begins by walking for a short period and then runs for the same amount of time. She takes a break before beginning to walk again. Consider the graphs shown. Okay. Let's look at the axes first. And let's look at the situations with it. Time is the x-axis, just like the last time here. This is the amount of time that has gone by. Time can't go backwards. It progressively goes forward. So no matter what Janelle does, x keeps moving. It keeps moving forward in that direction. Now, y is going to be a different scenario. Distance in this case, I'm going to say, is the distance that she ran. Not necessarily distance from an object. It's not distance from where she started, because maybe you could do something where you're running on a track, you know? And then you're getting back to where you started over and over. You should just consider that she's going on a straight path. Let's go ahead and say that. But this is how much she's covered. Now, which graph best represents the given situation? She begins by walking for a short period. And when you think about walking, you think about the rate at which she covers distance is not as high as, say, if she's running. So her change in y is not going to be significantly sharper than when she starts running. So I'm going to weed out A because that's a constant motion the entire time. She's going the same speed because she's covering the same distance over certain same time intervals here. Option B looks like she starts off going kind of fast. She covers a lot of distance over a short amount of time, and then she slows up. We're not really talking about that for option B. Option C looks like she goes pretty slowly here, and then it looks like she has run. Option C is in contention, and I think it's going to be it. Option D looks like someone who's just slowly picking up speed as you go. Something I'd imagine someone being able to do on a treadmill, that it's programmed to say start slow and ease into something more and more and more till you get to sprinting speed. So, okay, it looks like it's got to be option C. Now, how do we get this a little more recognized? Let's look at the intervals. And let's do this in, I'll use purple for this part. She begins by walking for a short period. Okay, that looks like it's covering the short period here that she is walking. I'll draw it in purple. And then runs for the same amount of time. Now, I wish that they gave us another graph where they did the walking first and then running like this, because it says runs for the same amount of time. I don't know if that really covers exactly that, but I don't know if there's something else that can tell us any different. Oh well, she walks for this many minutes and runs for this many minutes. I think the graph is a little off on that, but that's okay. Ideally, what I should see is that she ran for the same amount of time that she walked. So whatever this width in minutes is right here, this width would have been the same. That's what I'm looking for. Maybe all of them are wrong. She takes a break before beginning to walk again. She takes a break. Now this is in red. Now some people will have the idea and thought that she's walking here. Look, it's going to the right. Well, no, the distance hasn't changed. Her y value remained constant as time went on. And that's what it says. She ran, huff puff, take break. All right, for this amount of time, 10 minutes. I don't know what it is, but she's not moving. Like in a good way. Like not like she's not breathing. And she walks again, and you see again kind of this, I'm going to do it in purple again, this short strided, leisurely pace right here for that last bit of time she's walking. So it looks like C does cover it in the end, and we get to really interpret all those bits. All right. Now they're probably going to ask me, because 5 through 8, they're going to ask about, describe the other 3 graphs. And let me see the other questions so I know what's coming up. What if she began running into what are possible situations? Okay, it says what are possible situations for graphs A and D? I probably just mentioned them before. When it says describe the other 3 graphs, I'm going to kind of say what it was that she did. On number 8, we'll talk about why she could have been doing it. It's kind of hard to answer some of them. Describe the other 3 graphs. So ignore C. All right, graph A, I'm going to state that she was jogging. I'm going to say that for 8. Janelle moved at a constant pace. Okay? Hopefully that kind of makes sense there. She never changed stride the entire time. Looks like it's a little more than a walk, but a little less than a run. That's why I was saying jog. All right, B, situation B. What's she doing here? Looks like, especially compared to this run here, she's going really fast to start. Just full bore. She is sprinting. Janelle sprints, then slows. How about to a power walk? No, it's about the same rate as a walk. Then slows to a walk. She sprints for kind of a short period of time right there, and then she slows to a walk for a while. Takes a break because she stops there, as you can see. Then sprints again. She looks like she's dashing even faster. I wouldn't recommend this kind of workout regimen. I think you gotta figure it out a different way. All right, let's look at option D here. Trying to figure out a good color. So option D, excuse me, what's going on? Janelle's progressively speeding up. Janelle progressively speeds up over the entire period of time. Hold on. Janelle progressively speeds up. I need some water. One sec. I have a tickle in my throat. Sorry about my handwriting on this. Oh yeah, more of the A's losing. A's versus Rays. No. All right, progressively speeds up. So those are the situations described there. I think it works. All right, number 7. What if Janelle began by running, then slowed to a walk, stopped, and then began running again? Which graph? Well, I don't get why they said here, describe the other 3 graphs. I just did. So, you know what they could have been asking me to do? Just say, increasing, increase less, whatever. So, okay. We just answered this one. This is B. There, that saves time. I described it. So sorry if I'm not answering these to the best of the ability that's being asked, but you're getting a little more into it, which is good. This is all about interpreting it as real-life context. That is exactly what this is designed for. So I'm going to keep it on that one because we just talked about it. And number 8, what are the possible situations for graphs A and D? I kind of said it before. In A, a constant rate. What situation is Janelle actually doing? Probably jogging. And, I mean, why is she jogging? Just because that's her training or something like that? I'm just going to state jogging on that one. I think that fits the bill just fine. And then for D, what's a possible situation? And again, I think I kind of answered it in the previous one, but she's progressively speeding up. She goes from a walk to a power walk to a jog to a run to a sprint. How about that? But it's just easing into it fully. There's no intervals. It's not just, I'm walking. Okay, I'm power walking. It's I'm doing the slow walk into the faster walk into the da 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 da. You know, it just continues like it's like here. I'll call it treadmill routine. I don't really know what to write, but you heard what I said about it. She's speeding up more and more as it goes. It's like a car, you know. If you pedal to the metal. You can't start off going 60 miles an hour. You have to ease into it with that. Okay. That's kind of why I kind of like the treadmill routine thing. How about into a sprint? Because the treadmill doesn't start with ready, go, sprint. You'd really injure yourself badly. Enough talking with that one. All right, that was 5 through 8 for Janelle. Poor Janelle. Numbers 9 through 11. Next 3 problems. Here we have. During the winter, the amount of water that flows down a river remains at a low constant. Okay, sorry, I gotta absorb it. Okay, in the spring, in the spring when the snow melts, the flow of water increases drastically until it decreases to a steady rate in the summer. The flow of water then slowly decreases through the fall into the winter. Consider the graphs shown. Okay, because I'm not sure if we're going to talk about snow meltage or water flow or heat. I don't know. Okay, so here, all right, so we have seasons from winter to fall, and okay, I got it. So it would be nice to kind of diversify. I like A and D's graphs because we can kind of see moments where like we probably change season, where something like happens from one to the other. And I can do the same thing here, just it's not as obvious. So like maybe the first quarter is going to be the winter season, and then we have a spring season, and then summer season, and then fall season. I don't know if I really did this next one right, but that's okay. Yeah, that works. Okay, so, you know, we're talking about winter, spring, summer, fall, etc. So, which graph best represents the situation? So they said there is snow that melts. Well, let's look at it. Hopefully you know which one's spring, which one's summer. The amount of water that flows down a river remains at a low constant during the winter. Okay, so which ones, they said at a constant, but not only that, at a low constant. So which ones are constant during the winter to start with? It looks like A and D kind of take that into effect. So B and C, I think, are probably already out. These are rates. These are rates. This isn't how much water is going into something and filling up. This is the water rate. This is so many gallons per second, and it continues at a constant rate during the winter, and same with this one. Now, because they said at a low constant, I'm leaning toward A anyway with what they say next. In the spring, when the snow melts, the flow of water increases drastically. Yeah, so it looks like this is A right here. A constant, and look how it goes into a nice curve. You know, kind of the same thing as Janelle. She don't just bzz, bzz like that. She's going to progress into it maybe. And it's starting to rise there during the spring and increases drastically until it decreases to a steady rate in the summer. So it's got to slow up the rate again to steady out during the summer. This is working. And then during the fall, the flow of water slowly decreases. It's kind of quick, but through the fall, and I guess back into the winter again. So we're going to hit winter in the next year. So option A is definitely the graph that best represents this. I'm sure they're going to ask me about what these ones represent, and we can, I don't know if I can come up with something. We'll see. D looks like it's doing the exact opposite. So there's that. Okay, so describe the other three graphs. So again, I'll do it in graphing form mostly, but in B, and I'm not going to explain why, but in B, the water rate, the water flow rate progressively increases. Okay. Well, you know what? It does in C as well. In C and B, it progressively increases. This one, how about here? I'll say exponentially increases. Because what's happening here is this rate is just, it's accelerating. All right. You know the car example that I said before? Let's say you kept the pedal, you want to drive. And let's say you put the pedal, let's just not say to the metal for this thing, just halfway through, half throttle, not wide open throttle. Let's say that you put the pedal, you're stopped, and you say, pedal right here, and you keep it on there. Are you going to be driving at the same velocity the entire time? No. You'll still be speeding up, I guess, till you hit a point that you hit some velocity. But that's going to be what I'm going to call a progressive increase. That you put the pedal, boom, at 50% throttle, which is kind of a lot for cars. But you're going to be speeding up throughout that time. It's not like you just, boom, hit 60 miles an hour. But the acceleration is constant here. All right, this is going into more like physics, calculus kind of talk when I talk about this. The other version that I'm talking about is, say that this is my foot or gas pedal, whatever, and then I'm stopped, and I start by doing this as I drive. Pedal going into it to wide open throttle like that. I'm slowly accelerating through this. Not only is my velocity going up, but the rate of the velocity is now shooting up more and more. Maybe it's not going faster than the other one, but the rate of the velocity is now increasing because I'm now accelerating into it. And that's what option B is all about right here. Option B is this exponential increase. Maybe, I don't know if exponential is really the right term, but it's shooting up at a really wicked rate here because the flow, I really should just say water flow rate accelerates. I think that's really the best one to say. Accelerates. And sorry, I am talking through this with you for the first time. This is a teacher working out what he wants to say for his students. Okay, option C, this is the progressive increase in flow. Water flow rate increases. Remember, this is about flow rate. Gallons per second. Increases constantly. Basically, it's a constant acceleration. There's more flow, but it's constantly going up. And then D, this video is already going a long time. And then D here, high constant flow, because compared to the other one, it was low. Slowly decrease. It's basically the inverse of what happened in A. So I'm going to kind of read this. Into the winter, slow increase, not quite inverse, but slow decrease, slowly decreases to lower constant. Okay, whoop. And then we have a sharp decrease. I have to make sure I'm in my window. We have a sharp, I'm sorry about my writing, decrease to low point. Now, I could talk about the winter stuff, but I can't fit it. Then, sharp increase. Sharp INC. That works. So, okay, pretend like it's the winter. A lot of water flow in the winter. Once you hit the spring, it's going to slowly decrease to this amount in the spring. And then in the summer, it's going to hit a low water flow rate. And then in the fall, it's going to be increasing up back to here so we can get back to winter and do that again. Okay. All right, that works out. What are the possible situations for graph B, C, and D? Oh my God. So this part's hard. So option A was out because they already explained it. What are the situations? I don't know if they're stating like real world, what might cause this to happen. And boy, I'm going to have to think about, I have to be creative with it. B and C are kind of really hard to talk about because which one would be an acceleration versus something else? Let's pretend that in some sort of scenario, and I'm going to talk about C first. Let's talk about in some scenario in C, maybe it's just this weird, oh gosh, I don't know. Let's say like rain, like strange rainy season. We had a really rainy year, and it just rained the entire year. A constantly rainy season. Constantly rainy year. There's no water flow in the beginning. It starts raining, you start getting minimal water flow. That rain continues the entire year. That's the only way I can explain it. The rain continues throughout the entire year, and you're getting more water flow as you're getting more water, and there's just a constant rain throughout. Boom, that works. I don't know if that's what they're asking. I'm sorry about this. Option B, what could make it like accelerate? The thunderstorm just keeps going up, up, up. I guess you could say something like that. Maybe something about, I don't want to be like morbid, but like a flood, a year-long flood. Let's do it this way. Let's say the option B is more of a, this was about snow melting. Let's talk about like ice melt. Like, let's talk about snow meltage, but let's say that there wasn't. This is down a river. Let's say there wasn't a river, and a river was kind of created. What's different between option B and option A here? There is no water flow to begin with. Maybe there's no water to begin with. So in option B, let's talk about something, let's just say mountain, snow mountain. Whoops. Meltage. And I don't know if this perfectly works for the scenario because I don't know if there would be a higher rate in the fall than in the summer. So I don't know if that works perfectly. But it's been warmer for longer, so it's likely that at least you'll get more water coming down as it's melting throughout. Because in the winter, all the snow is going to be intact. And once it starts to get warmer, you're going to start to get more flow. I assume hotter weather would get more flow, but you do have warmer ice in this moment where you'll probably get more melting. I don't know if you've probably used that kind of scenario with like a water cup and seen when it melts more. Ice will melt faster when the temperature of the ice is warmer. So if I'm over-explaining. Option D. Okay, so what could cause option D? So we have high water flow in the winter, and it slows up in the spring, more so in the summer, and back up in the fall. Okay, so this kind of works. Let's pretend that this is a river that, and I'm not saying pretend or not pretend. Let's pretend that this river doesn't really get a lot of water runoff from something, like maybe it was a drought kind of year where there was no rain. So maybe during the winter, because the water's not going to evaporate, maybe there's just nice water flow in the winter, and going back here, maybe it rained again, right here. But here in option D, no rain. And then you kind of let evaporation kind of take place, or very little rain, and then evaporation through summer, and then a rainy fall. Okay, sorry for being a little over creative with some of these. These questions aren't really as big of math-based stuff, but it is important to make sense, especially those ones. But it is important to make sense that these things can be real world, and we can have a description that ties in with it. That's what the whole thing is on, graphing representations. All right, so let's go ahead. 2 children are selling lemonade. They are charging $1 for a cup. They only sell 10 cups. Consider the graphs shown. So every problem we've seen so far has had to do with time, even the seasonal one. Time is this progressive, ongoing. There is no sort of break or lapse in time for anything. We could record specific times, but something's always happening at every microfraction of every second. So those are continued to be very continuous. We've seen continuous graphs so far, something where I don't have to lift the pencil from the paper when I'm drawing it. Now we see two other graphs here that could be considered to be what's called discrete. I think I said consider twice. Discrete has very specific, fixed, separated points that are a single whole value. It doesn't have to be a whole number, but a single one item value. There's no interval. It's elements. It's numbers of items. A and B are called discrete graphs here, and C and D are called continuous. Now, C and D normally more often occur with a sense of time because it's something that's progressively ongoing. Other things can occur too. Now our X is number of cups, and two children are selling lemonade for $1 a cup. My guess for these particular children is they fill up the cup, they sell the lemonade. They're not going to fill up half a cup. So when you're talking about selling cups and making profit, A and B are kind of the ones that talk about selling a cup at a time. I sell a cup, and this is how much money I have after that many cups sold. So you can consider a number of cups. This could be 1, 2, 3, 4, etc. And it continues, and then they make $1 a cup, $1, 2, 3, $4. And it looks like it's going to be A. Which graph best represents the situation? I think it's A. You're constantly making more money the more cups that you sell, and it's going at a constant rate. Another dollar for another cup. Now C kind of matches it if it were more in, I won't say liquid form, but that you could sell any sort of fraction for your cups there. B is a little different scenario. You're not making a constant amount of money with it. So, and we're not talking about profit. Oh yeah, we are. We're not talking about net thing, like maybe you're spending more for operational blah, blah, blah. We're not talking about that. So A works for this one. Of course, I forgot about this. What situations could the other graphs represent? All right, what could cause B, C, and D? I guess is what they're asking. The first thing that comes to mind with B, there are two things that come to mind. One thing that comes to mind is you sell cups at some rate. It seems it's kind of constant. And over time, you notice that there's a dwindling amount of customers. Maybe there are so many people that are there and you're like, oh, people aren't coming. And you start reducing the price. That's something that I'm thinking of for B. Something like price reduction over time. Ooh, I have another thought. Another one, which doesn't really, I mean, obviously this isn't the situation anymore. Another one with the lemonade selling thing is paying in bulk. And you might understand this scenario, paying in bulk. What I mean by that is the more lemonade that a customer buys, the better deal that they're getting. And you've probably had this before. If I go to Redbox and I want to rent a Blu-ray, I can have one night for $2 or 2 nights for $3.50. Or it's 2 or 3 nights or something like that. The point is, they're not going to say, well, just give us another $2, because I could just hold on, like, you know what I mean? I could just rent it again, and they're trying to incentivize you to keep it another night for a better deal. Same thing with like pizza things, a small, a medium, a large. It's not always linearly proportional. They're going to incentivize you to get more pizza because they want to get more money, but they're giving you a better value out of it. And customers understand that, and they're willing to pay that. I always am as well. So just keep that in mind. Like a 6-inch sandwich isn't always half the cost of a foot-long sandwich. See what I mean? So buying in bulk here could be a scenario where you're saying like, all right, you buy 10 lemonade cups. I'm not going to charge you much more. Well, this flattens out pretty fast, but I'm not going to charge you much more than otherwise. Does that make sense? So there's that. Option C. Now, option C is a lot like option A, $1 a cup. The difference is this one's continuous. So maybe in this case, maybe they're willing to sell fractions of a cup, and they have a way of like weighing it to determine half a cup weighs this much, because it's all about density-ish, or volume. So, or they just have a way of just charging it and just going, oh, that much? Okay, that much money. So they are charging for fractional cups as well, for fractional values. So this kind of helps explain, this kind of helps explain that, you know, over time they can sell fractional amounts with these things, and you can get a continuous representation there. If that's kind of making sense there. D would be a continuous something about Oh boy. I don't know how to explain D for this. Basically, they're not profiting. They're giving it away for free. And I don't know if I can explain D in a real world scenario. But basically what's happening is no matter the number of cups that are being sold, fractional or otherwise, they're not profiting. Maybe it has to do with them spending a certain amount and not getting a certain amount back. Like they're spending $1 to make it and they're charging $1 and the fractional amounts. I'm going to leave that be. I'm working overtime here. All right, number 14, is the graph that represents the given situation discrete or continuous? Now, why did they just ask that now? We talked about that so long ago. If they're talking about this one, I'm going to say it's discrete because it's option A. This has to be a discrete one as far as $1 for a cup, assume a full cup. It's discrete. I'm moving on. All right, a plane takes off and climbs steadily for 15 minutes until it reaches 30,000 feet. It travels at that altitude for 2 hours until it begins to descend to land, which it takes 15 minutes at a constant rate. Obviously, I'm not absorbing it much, but what I can clearly tell is we're going to draw a graph this time. Before we interpreted graphs, now we create them. Sketch a graph of the situation. Okay, so we have the height of the plane in feet. Obviously, this is altitude. This is going to be 0 feet right here, so that's ground level. And the time in hours. They talked about minutes in here. So understanding that 15 minutes is a quarter of an hour, I'm just going to put 15 minute right there just so you can make sense of it. Every one of these is another 15 minutes. You feel? Okay. So a plane takes off and climbs steadily for 15 minutes. I assume that kind of means constant rate. So I'm going to go ahead and use a line here and say, at a constant rate, it's going to climb for 15 minutes until it reaches 30,000 feet. I don't know if that's reasonable or not to do in 15 minutes, but we'll take it. It travels at that altitude for 2 hours. Okay, so at that altitude means it's going to stay at this constant height. That's fine. Now, where do I stop this thing? Do I stop this at hour number 2? You have to be careful. It says it travels at the altitude for 2 hours, not until 2 hours into the flight. 2 hours since the 15-minute mark. So this plane, 2 hours after 15 minutes in, is 2 hours and 15 minutes in. It's going to go to this bit right here. This is a 2-hour stretch right here. Okay? That's where it's constant. Until it begins to descend to land, at which it takes 15 minutes at a constant rate. So, I don't know. I guess they're saying it lands within 15 minutes. This isn't realistic for a plane, but that's okay. Let's make it blue. It's going to descend to land. I assume it's going to be right there. That's a scary plane flight. You could probably make it curve off. That's probably more realistic. The plane doesn't just do this. Out like that. That's fine. This works. I'm accepting. Not so real world, especially even in the situation, but this works. You understand where the 2 hours come from. Okay, is the graph discrete or continuous? Well, I just drew it continuously, and the main culprit of this, the main thing that explains it is time. If time is being observed, time continuously happens. And almost I can't think of a time scenario that doesn't have a progressive flow to it. Because time is always able to be measured. Even if you're not measuring it at the instances, that thing is still happening. So you have to keep that in mind as well. Determine the domain and range. Okay, first time we're looking at domain and range. Domain is telling us what x values occur for this thing. What time frame are we looking at? And I can say it in words or use what's called like a compound inequality because it's a continuous function. I can state what the time interval was. So I'll state the time interval in words and in math form. In words, the domain says what time frame did we go for? We went from and this says it's in hours. So I'm going to say from 0 to 2.5 hours. And I say 2.5 because we landed here, which is a quarter of an hour, half an hour right there. From 0 to 2.5 hours. Or on X, I'm going from 0 to 2.5. If you've seen compound inequalities before, remember this is measured in hours. This is how I can represent it. These are all of the X values that are used. And it's every single one. All of these, point. All the X values are used. This X value has a point right there. Stuff like that. Range is going to be the other guy here. Range is going to be for the Y values. What Y values existed in this graph here? What are the feet, essentially? And I can say the plane took off and landed, And so it hit 0 feet for sure, never went negative, and it went as high as 30,000 feet. So I can say from 0 to 30,000 feet. As far as arrange it as a compound inequality, I can do the same thing as I did on x, from 0 to 30,000 with all the y values in between, and including 0 and 30,000. That would be the domain and range of this particular setup right here. Okay, here we go. Moving on. 18, 19, and 20. These actually, let's see. I think these, okay, 21. Okay, there are 22 problems. So 18, 19, 20. A contestant on a game show is given $100 and is asked 5 questions. The contestant loses $20 for every wrong answer. And you can see they broke it down for us. Amount of money the contestant has, number of incorrect questions. Sketch a graph of the situation. Is the graph discrete or continuous? Determine the domain and range. All of these are kind of answered within domain and range. We can probably establish domain and range before, especially domain, I think. But we can well, both. We can establish these in terms of drawing the graph. Is it discrete or continuous? Well, here, can you have half of an incorrect question? Is there something between question number 0 that's incorrect, or question number, the first question you get incorrect to the second question? And I'm going to say no. This is going to be discrete. This is going to be discrete because there are specific points. There's not a flow of losing money here. There are moments of losing money, and it's for every wrong question. And I can even probably label this a little bit. I'm going to call this first point, when there are 0 incorrect questions had, the $100 mark. And this is in dollars right here. The contestant loses $20 for every wrong answer. This doesn't say number of questions right here. I don't know when they got something incorrect, but this graph will model, if I get one question wrong, I'll have $20 less than before. So I'm going to have $80. Whoops, I shouldn't put it there. So I'm going to have $80. Let's put it right here. $80 at that moment. I probably really should have gone the other way. Now that you can see, it can go down to 0. 80, 60, 40, 20. So 40, 60, 20. Now notice again, this is a discrete in 0. This is a discrete graph. Discrete because I can't have a moment where I'm going to have $90. Think about it that way. I can't have a moment where I'm going to have $90. I have 100, and I can either keep the 100 or lose 20, and then lose another 20, lose another 20, whatever like that. I can't lose just 10. After a second question wrong, I'm going to be down at $40. And sorry if these aren't perfectly lined up. I'm not going to plot a line anyway. But it's linear. After I missed my third question, here, $60. Missed my fourth question. What did I write here? Did anyone notice that? You're like, 60, 40. I said that wrong too. After 4 questions wrong, $20. And after 5 questions wrong, I lost all my money. Okay. Now this shouldn't look like a curve. It should look like a line. So let me try that again. There we go. A little better. Okay. So there is the graph that's representing it. Now it's discrete. It says describe the domain and range. Now keep in mind here, the difference between this problem and the last problem is that although I can go from 0 to $100 and 0 to 5 questions wrong, this is discrete, which means I can't say this, and I'm going to write it in red. I can't say I'm going from 0 to 5 on x, because this interval implies I can be any x value in between, including 0.5 and 2.7 and things like that. You can't have those moments, so we can't state an inequality. Although x only can go between 0 and 5, there are specific numbers that the domain can represent. So in terms of determining the domain and range, and I'm gonna state it out loud as I do the math version here. The domain is this specific set here. I can have had 0 questions wrong, 1 question wrong, 2 questions wrong, 3, and I know this sounds mundane, 3 questions wrong, or 4, or 5. You can't have 6 questions wrong. You can't have half a question wrong. You can't have negative questions wrong. These are the only possibilities within your domain, the x values for number of incorrect questions. That's what they are. And I'm going to write them both in order, even if it goes the other, whatever way. The range is going to be the same kind of idea. What possible ways can we describe how much money I can possibly have in any situation? It's not just 0 to 100. It's the specific dollar amounts. I can have 0, and I'm not going to put the units. I can have $0 remaining, I guess, $20 remaining, $40 remaining, $60, $80, and $100 remaining. These are the possibilities I can have. These don't necessarily tie in like the 100s with the 5. No, 100 is actually with the 0 if you think about it. That's where you would plot coordinate pairs. But I'm listing these in order. It's a healthy way of going about doing domain and range to make sure you've included all your values. And it sounds better from 0 to 100, like that. But these are the only elements of the range and the only elements of the domain. Nothing in between, nothing outside of. Okay. So there's number 20. Last one, number 21 and 22. You decide to take a hike. You decide to hike up a mountain. You climb steadily for 2 hours, then take a 30-minute break for lunch. Then you have to draw this. Then you continue to climb faster than before. When you make it to the summit, you enjoy the view for an hour. Finally, you decide to climb down the mountain, but stop halfway down for a short break. Then you continue down at a slower pace than before. Okay, I'm going to use the line tool for this one. Now this thing, notice that they did give us intervals for time. They did not give us height for feet. So I'm going to do what I do for height. I'm not going to give you a certain amount of feet, but we do know when we're going up, down, and staying the same. So I'm going to make sure to note those with the lines, but the time does matter. Let's count how long we go for. You climb steadily for 2 hours. Take a 30-minute break. That's half of an hour. Then you continue to climb faster than before. It doesn't state, some unknown, but faster than 2. Less than 2. We make it to the summit. You enjoy the view for an hour. You climb down the mountain, stop halfway for a short break, and then continue to climb down at a slower pace than before. How about slower pace is more time? So how about we say greater than 2, just to kind of change it. So that's 6, 7, at least, let's go about at least 8 hours total. Pretty long hike there, 8 hours. So I'm going to make sure that I put intervals for that to work that out. 1, 2, 3, 4, 5, 6, 7, 8 hours in. All right? Hopefully that works out, and I'm going to use this to construct portions. The height, not as important, but I'm just going to use the line tool to make sure I can get certain lines flowing on this thing. Okay, you decide to hike up a mountain. You climb steadily for 2 hours, then take a 30-minute break. So I'm going to climb steadily, and I'm not going to make it too sharp. I'm not going to go to the top. You climb steadily for 2 hours, then you take a 30-minute break. So 30 minutes after this is just a half of an hour like that. 30-minute break means I'm not climbing at all or I'm not descending, so it's constant. Then you can continue to climb faster than before. I want to make sure that this climb right here, who cares how high it goes? It's about how long I go. I make sure that my climb does not exceed a 2-hour stretch. I can't go all the way to 4.5 hours here. I have to go less than it in some capacity. I'll go to the 4-hour mark. By faster than before, well, actually, the slope does matter, doesn't it? You know what? It says faster than before. It doesn't say shorter than before. So I take back what I said. However, okay, fine, I'll do that. I can go beyond 2 hours. No, I'll do this. I'll go to hour 4. I climb faster than before. I'm a steeper slope. When you make it to the summit, you enjoy the view for an hour. I'm on hour 4. I enjoy it until hour 5. Finally, you decide to climb down the mountain, but stop halfway for a short break. Then you continue down at a slower pace than before. Okay, I'm going to go down the mountain kind of at not a super rigorous pace, but I'm going to go down the mountain. I need to make sure I get to the bottom by 8. So let's say I'm going, it's pretty rigorous. Right here, yeah, because I got to make sure that I get down that mountain again. You know, this can be symmetric. I can do something like that. Stop for a short break, and I go down slower pace than before. Okay, that works out right there. Kind of symmetric. I climb steadily, take a 30-minute break. I climb steadily for 2 hours, take a 30-minute break. Climb at a faster pace than before, steeper slope. It doesn't mean it's a steeper rate of the mountain. Just I'm going faster over a shorter duration of time or whatever. I stop for an hour, from hour 4 to hour 5. I go down at some pace. I take what I consider a short break, and then I go down slower than the pace that I started at. Cool. Now notice this was time, and the way that I drew, you notice how I didn't do points only? I continued this path because you can track me at any individual moment. So is this graph continuous or discrete? It is most definitely continuous. Again, time is definitely a big factor to that. I wish we had more problems that were giving us something with regard to time that could tell us a little more in the lines of like these, other than time that says we can do this for continuous. You kind of saw instances of things that can have fractional values, and you're going to run into some more, I guess, over the course of time. But time is always a key thing in a lot of word problems, and when you have time, you probably have a continuous function. All right, that'll do it here. I just hit the 50-minute mark right now. I know this went over long, a lot of conversation, a lot of me talking, but hopefully you made sense of what it is that you just heard, and because this teaches you it. It teaches you it at the same time that you did it. It might have taken you a while to come up with some of these answers anyway. All right, so that'll be it. Thanks for watching, guys. Take care.